This
module.
conference will now be
So
recorded.
at first we have just done one single class of the microcontrollers module, and we started initially with the definition of embedded systems, which is nothing but a combination of hardware and software which is doing a specific task. Then we tried designing an automatic gate opening system, which was a highly uh, purely hardware based device, and we did not consider it to be an embedded system because software was not installed. Not involved. Then we saw the examples of embedded systems. We listed some of them. We saw some in the slides as well. Then we looked into the categories of embedded system. First one is standalone embedded system, which is further divided into slave standalone embedded system and independent standalone embedded system. Semi-automatic washing machine and microwave ovens are slave standalone embedded system. Fully automatic washing machines, automatic cars are an example of independent standalone embedded system. Then the embedded systems which will take action in the real time, they are real time embedded systems. Examples are airbag system, the robots, the brake system, fire alarms. And coming to the networked embedded system, the devices in the embedded system are interconnected to each other, wired or wireless. Example, home automation and the ATMs. Then we have mobile embedded systems which are capable of moving. Examples are robot, Google car, and drones. And apart from these, we also had a category called hybrid embedded system. So whenever an embedded system belongs to more than one category, we put it under hybrid embedded system. A good example is Google car because it gets involved in all of this. Then after that, we started with the very important component. Okay. What is the difference between real-time embedded system and independent standalone embedded system? Okay. Now you can distinguish between the two. They are not same in fact. So when it comes to independent standalone embedded system, they will have an intellectual part. So fully automatic washing machine is one such example, and that doesn't belong to a real-time embedded system. Okay. So because you need not take the action on real time, so it is fine to take the action even you have switched it on later, or maybe it doesn't have a particular deadline as such to be met while taking the action. So real-time embedded systems are the one which responds according to the real time, depending on the situation. So brake systems, airbag systems, and some of the times there might be a scenario which has to work according to real-time changes like temperature, like humidity of the soil and all. They all belongs to real-time embedded system. So both of them are quite different. I wouldn't say they are exactly same. Okay. So independent standalone embedded system is a system which is capable of taking the action on its own. So real-time embedded system is the one which is supposed to be taking the action in the real time. So drone is not a real-time embedded system. You don't end up taking the action on a particular time itself. It is okay even if it doesn't work on that particular time. Okay. Okay, but all robots are not real time. They also work on commands. Yes, not all the robots are real time. Okay, so I do agree. So I've just put it as a simple example. If you want, I can take it out. Like all robots are definitely not real time embedded systems. Okay. Which controller we are going to study? So it's a PIC microcontroller we are going to study. Real-time air defense system, yes, that can be a real-time embedded system. Okay. All right. So after that, we started with the components of the embedded system. And to start with, the very first component we discussed was microcontroller or microprocessor or SoC. So if the functionalities are going to be more, Okay, if the functionalities we have to implement are more, which cannot be taken care with a single individual microcontroller, we might need multiple microcontrollers or microprocessors. And SoC is just nothing but system on chip, which will have multiple microcontrollers or microprocessors embedded on a single chip. So as the number of functionalities increases, you may need more number of microcontrollers or microprocessors. That is when you're going to choose SoC, which is the very first important component. Then we started with memory. So we were discussing the types of memory in the previous class. So first one is ROM, which is called as non-volatile memory. So it is a read-only memory. It has three categories. One is PROM, programmable ROM. So EPROM, erasable programmable read-only memory, and masked ROM. So PROM is also called as one-time programmable because you will be allowed to write into the memory for only once after it is being manufactured. So example is in the toy industry. Then EPROM is erasable programmable read-only memory. But in order to erase, you should be using the UV rays, and hence it is erasable programmable read-only memory. So we are going to use it in the R&D department and the research labs. And then we have got as masked ROM, which is MROM. So after it has been manufactured, you will not be allowed to write into that memory. So bootloader is one such case where it is written on the masked ROM, and you should not be allowed to change any contents written in the masked ROM. Then we have RAM, which is representing random access memory, which is a volatile memory. So once the power is lost, you are going to lose the data. We have two types. One is SRAM, the other one is DRAM. SRAM stands for static RAM, and the example is cache memory. DRAM stands for dynamic RAM, which is the main memory in case of all of our devices. Then we cannot work with just RAM and ROM, which is why we have a hybrid memory. There are two types of hybrid memory. One is EEPROM, the other one is flash memory. EEPROM stands for electrically erasable programmable read-only memory. So the advantage of EEPROM is you can have the data returned for any number of times. You can keep rewriting the data in case of EEPROM. And to erase the data, you can erase it electrically. But the problem with the EEPROM is it has a very slow writing speed. So to write into one cell, I would say to write 1 byte of data, it approximately takes 5 milliseconds. So it consumes more time to have the data returned. But because of its extensive use these days, so there are some improvements being made, some advancements being made on the EEPROM also. And these days it takes 5 milliseconds to have a data return to one page. And the size of the page can vary from 8 bytes or more. So up to this, have you got any doubts? Any doubts in the memory up to this? Okay. Now proceeding ahead, the next we have got is flash memory, which is further divided into NOR flash and the NAND flash. So each of the flash has its own advantage and disadvantage, but understand flash is a very commonly used memory. So it has been recorded. Don't worry, recording I have started. So flash is like the very commonly used memory out of all the memories which are available. And each of the flash, I have a NOR flash, I have a NAND flash. Each of the flash has its own advantage and disadvantage. Now coming to the NOR flash, it allows less density and it offers us more reliability. Okay, so I would say less dense and more reliable. Okay, but when it comes to the NAND flash, it is more dense but less reliable. Okay, now what do you mean by dense? What do you think the dense means? Okay, now let me show you what the density means. Assume there is a chip of 1 centimeter square. Okay, a chip of area 1 centimeter square. I have taken a chip which is of area 1 centimeter square. Now in this 1 centimeter square area of a chip, if I can store only a certain kilobytes of data, I would say less dense. And if I can store more bytes of data, let's say some gigabytes of data, I would say more dense. So dense means populated. Okay, so capacity, I would say in short. So in 1 centimeter square, if I can store several kilobytes of data only, then we call it as less dense. And in the same space, if I can accommodate more GBs of data, then I would call it as more dense. So NOR flash is less dense, but NAND flash is more dense. In the same area, if you use NOR flash, it allows you several kilobytes of data only to be written. In the same area, if you occupy a NAND flash, it allows you several gigabytes of data to be written. Along with that, we also speak things with respect to reliability. So reliability means something trustworthy or how guaranteed it is. So if you have the data return in NOR flash, it is more reliable, so more guaranteed. And if you have the data return in NAND flash, it is less reliable, so it is less guaranteed. Now I'm going to give you an option. Okay, the option is, assume you are given with a code and a data to be stored. Okay, so you are given with a code and a data to be stored. So where are you going to store the code? Out of the NOR flash and NAND flash, where are you going to store the code and where are you going to store the data? So between NOR flash and NAND flash, which one will you choose to store a code and which one will you choose to store a data? Can you please answer? Okay, so code in the NOR flash. Okay, so many of you are saying code in the NOR flash and data in the NAND flash. Okay, yes, fine. Now, in order to understand this, you first have to decide which among the two is more important. So, between the code and the data, which among the two is more important? So, code, let's say, is the basic program which is running in your device. So, just take an example of your mobile phone. So, code is a program which is running in the background. Data is like the pictures, the selfies, the files you're going to get stored in your mobile phone. So assume your mobile phone is made up of both NOR flash and NAND flash. Where are you going to get the code stored and where are you going to get the data stored? So to, to make that decision, in fact, you have to decide which among the two is more important, whether it is the code being important or the data being important. Which one do you think is important between the code and the data? So data is very important. Okay. Now, if data is important, why don't you store it in the NOR flash? Because I want it to be more reliable. So if data is important, why don't you store it in the NOR flash? Okay. Now for that, again, I'll go with one more circumstance. Okay. So I have code, I have data. Now assume you're going to buy an iPhone. Okay. So just an example, a simple scenario, you're going to buy an iPhone. So the iPhone you're going to buy is to obviously store some pictures of yours, some files of yours, some data of yours. Now assume at some point of time, okay, so you have invested around 1 point odd lakhs of money on your phone, and at some point of time you're going to lose the data. Will you be fine with it? So it's like you have got a data stored inside your mobile phone. Okay, so you're not fine as of now. But if you're losing the data, don't you think you will have a way of retrieving the data back? So generally, whenever you are having some data, you will keep it backed up in your drives or you will have it backed up in some cloud. So generally, some of the important data, you will have the ways of retrieving it. Now, assume the same scenario. You have bought a iPhone and your code is getting corrupted. The code of your iPhone is getting corrupted. So the iOS which is running in your iPhone got corrupted. Now tell me, are you okay when your code is corrupted and your iPhone is not working fine? Is there a way of retrieving the code back? Like if the code itself gets destroyed, your complete investment on the phone is lost. Okay, so you're knowingly losing around 1 point odd lakhs of money which was invested on your phone. So always remember, between the code and the data, it is always code being very important. Okay, so there are ways of retrieving the data if you have lost it, but retrieving the code is quite difficult. So code is more important and data is less important comparatively. So I am going to store the code in the NOR flash and data in the NAND flash. And one more obvious reason is, if you take your phone, okay, so there will be code already running in your phone. Hardly how much memory do you think your code is occupying? Out of the overall memory available, hardly how much of the memory is the code occupying? So generally a few MBs, or these days it can occupy 1 or 2 GBs max. Okay, so your complete code might occupy only around 10% of your complete memory available. I would say not even 10%, it will generally be 1 or 2%. So code is comparatively smaller in size when it comes to the data in all the devices. So I want less density anyways, because it is not of enormous amount. So code will be always stored in the NOR flash and data will be stored in the NAND flash. And one more reason for code being stored in the NOR flashes, there is a feature called XIP which comes in all of the NOR flash. Okay, so there is a feature called XIP which stands for execute in place. Okay, now I have a question here. I hope you people are done with your C module, right? You people are done with your C module. Okay, so where did you get your .c files stored? Where did you get your .c files stored? All of your .c files stored. Where did you get? Present working directory. Can I say that it got stored in your hard disk? Can I say all of your codes were stored in your hard disk? Okay, yes. Then along with that, so when you had to execute the code, okay, so there is ./a.out what you provide to execute the code. Now, when the code is getting its time for its execution, it was getting certain bytes of memory. Do you remember that? Which was splitted into 4 segments: the code segment, data segment, heap segment, stack segment. Do you remember? Okay. Where do you think that memory was allocated? In what memory was that bytes of memory allocated? Yes, that was in the RAM, in fact. Okay, so all the memory was allocated in your RAM. Whichever code you're running, code was actually stored in the hard disk and it was getting executed on the RAM. So in the RAM, in the code segment, your code was rewritten. Your executable code was rewritten. So whenever you want your code to get executed in your system, it had to be brought to the RAM while it is getting executed. So that was a disadvantage. But if you get a code stored in the NOR flash, we have an option of execute in place. You don't have to bring it to the RAM for its execution. So if the code is stored in the NOR flash, it can get executed there itself. Okay, that is another advantage of NOR flash. So NOR flash is the one which is chose to store your code, and NAND flash is the one which is used to store the data. So these are the types of hybrid memory which comes under flash memory, a very commonly used memory: NOR flash for code and NAND flash for data. So this is about the types of the memory we have got to be selected in an embedded systems design. Any doubt with this? Okay, so Manjunath Swami is asking, and with respect to mobile, it's in MBS. In other controllers, will it be in kilobytes? Okay, so it depends on how your code is being written. I wouldn't say it will be kilobytes all the time. It completely depends on how lengthy your code is. Okay, if you write an optimized code, it can be in kilobytes, it can be in just bytes also, not even kilobytes. That is also possible. It depends on the application for which you are writing the program, and it also depends on for what reason, how lengthy your code actually is. I'm in mobile, which is the ROM. So it depends on the configuration of your mobile. So you cannot identify which is the ROM, which is the RAM. So, as I'm saying, it is generally the flashes which are being used. Okay. But there will be a mass ROM available in all of your devices which will have the bootloader written. So even your Android OS, I would say, might have got written in your mass ROM. Okay, for the sake of safety, that no other process is overwriting your program. Okay, so that is possible. Or it might have got written in the NOR flash also, because it has got an option of execute in place. So it completely depends on the configuration you are buying. Okay, so that was about the second most important component. No, so finding out the size, I would say these days, if you open the storage of your mobile phones, it clearly directly says the total memory. So in some of the cases, you will get the differentiation, okay, like how much is the size of the ROM or any other category of memory available. In earlier cases, we used to get it size of the cache memory or size of the RAM and all, but these days it gives you a cumulative memory. It generally shows you the total memory available in your device if you look at the storage. Okay, so finding the size of each type of memory available in your device is quite challenging. Okay. All right, so let us begin with the next important component. So please understand that SoC or microcontroller or microprocessor is considered as the heart of the operating system, sorry, heart of the embedded system, and memory is considered to be the brain of the embedded system. So they are like the most two important components of the embedded system. Apart from this microcontroller and memory, what else do you think is the next important component apart from these two? Size, what? Input output devices, okay. Timers, peripherals, drivers, powers, okay. So all of this, I would say the next important component for any embedded system to be designed is a sensor. Okay, so power supply, I understand it's a important component, but we are coming one after the other. The next important component is sensors. So ports are something which comes in your microcontroller itself. Okay, so ports comes in your microcontroller itself. Then counters, the timers, some drivers will also come in your microcontroller itself. Communication protocol, yes, it is important when you have to communicate between two different chips. Okay, that is really important, but we are as of now looking into the components, the hardware components. So the next important component is the sensor. Now, sensor is like a very important component of any embedded system. So you may have to sense one or the other thing in an embedded system. So sensors are really important. So sensors are going to sense the signal and they are going to give an analog output. Okay, most of the sensors are going to give an analog output, and your microcontroller or microprocessor cannot work with just the analog signals. So they all are digital. They can only understand things in terms of zeros and ones. So any microcontroller or microprocessor you take can understand things in terms of zeros and ones only. So when sensors are sensing the signal and they are giving you an analog output, so that analog output cannot be directly fed to a microcontroller or a microprocessor. So you may need an intermediate in between, which are called as ADCs, and they stand for analog to digital converter. So the sensors, whatever analog value they give, have to be converted to a digital value, and then it has to be given to the microcontroller or the microprocessor. So this ADC can be built in some of the microcontrollers, or in some of the cases you may have to externally connect it. So it completely depends on the microcontroller you are choosing. But sensors are going to give an analog output which have to be converted to a digital value before it has been given to the microcontroller to take any action. So ADCs are always required between the sensors and the microcontrollers. After this, the next important component. So sensors are sensing and giving you a signal. Your microcontroller is consuming that signal. What should a microcontroller do after sensor senses and gives you a value? So according to whatever sensor senses and gives the value, your microcontroller should take the action, right? So according to the input it is being taken, yes. So your microcontroller have to take the action, for which we need the next important component, which is the output device called as actuators. Okay. So we need actuators to take the action. Now again, actuators are analog devices. They are going to work with analog signals. So your microcontroller always takes a digital value, gives a digital value. So when microcontroller is giving a digital value, your actuator cannot work with a digital value directly. So we need another intermediate called DAC, which stands for digital to analog converter. They convert the digital value to the analog value and then provide it to the actuators. And again, these DACs can be built in some of the microcontrollers, or in some of the microcontrollers, you may have to add them externally. So sensors sense the signal. Okay, it's like a closed loop. Sensor sense the signal. It gives you an analog value, which is further given to the ADC to convert it into a digital value. That digital value will be taken by your microcontroller. So after your microcontroller takes that digital value, so it makes some comparison, and according to that, it makes a decision to take the action with respect to the actuator. So they are output giving devices. So actuators are analog in nature. Some of the actuators will be analog in nature. So DACs have to convert the digital value to an analog value before it is being given to the actuator. For example, if you take a temperature sensor, so the sensor is going to sense the temperature and it is going to give it to the microcontroller via the ADC. If the temperature is more than that of the threshold range, then using the actuator, we are going to turn on the fan. So it is like a closed loop system. The second arrow are showing directly connection to SOC without going to ADC and DAC. So as I'm saying, ADCs and DACs can be built in some of the microcontrollers. Okay. So if the microcontrollers will not have ADC and DAC built in, then you have to externally connect it. So the direct connection literally says there can be some ADCs and DACs built in the microcontrollers itself. Got it? Does PIC microcontroller has a built-in ADC? Yes, it has. So you will understand when we look into the features of the PIC microcontroller. It has ADC built in already. Okay. Next, apart from sensors and actuators, okay, means it is not required for all. No, most of the sensors, I would say 99% of the sensors are analog providing sensors only. Okay, so ADCs will be built in and it is going to convert the analog value to the digital value. So most of the sensors will be needing a ADC for its for the analog value to be converted to a digital value. This ADC can be built in the microcontroller or you may have to externally connect it to the microcontroller. That is what it means. Okay. So the next, are we going to learn to read the data sheet of different microcontrollers? So I will make you understand how to read a data sheet of one particular microcontroller. That should be helpful in reading the data sheet of any microcontroller. Okay, so whatever we learn will be in a generic manner. Just to show you an example, we will focus on one particular microcontroller. But whatever we apply on this particular microcontroller's programming is going to impact the same way in any of a microcontroller you choose. So we will in fact learn things in a generic manner, but focus on pick microcontroller as an example. Okay, so whenever I'm speaking anything regarding a microcontroller, I will keep the example as pick, but the things work the same in most of the microcontrollers. Okay, so proceeding ahead, the next important component is human interface. Okay, so it is really important that the human interfacing is possible for any of an embedded system. So let's say I want to give an input to the embedded system I have designed, or an embedded system wants to show some certain scenarios to me as an output. So I do need a human interface between the human and the embedded system. And these human interfaces can be as small as an LED or it can be as big as an LCD also. Okay, so human interfaces are like one of the important component. Apart from human interface, we are also going to make use of FPGA or ASIC. It's a very rare scenario that we use FPGA or ASIC along with all other components in an embedded system. So it can be a part of the embedded system. Is there anybody who knows what does FPGA or ASIC stands for? Yes, FPGA stands for Field Programmable Gate Array and ASIC stands for Application Specific Integrated Circuit. Okay, so ASIC stands for Application Specific Integrated Circuit. Now, FPGAs are as I said, as the name says, field programmable gate array. It is going to have a combination of gates arranged in a particular manner to perform a specific task. So, FPGAs are like the dies for the product you are going to design, and FPGAs are comparatively cheaper to design when it is compared to ASICs. So ASICs are like comparatively costlier to be designed. So whenever you are planning for an ASIC to be involved in an embedded system, we suggest you to reprogram the FPGA as many times as you require. And once the design is finalized, you can convert it to an ASIC because making changes to an ASIC is costlier. So any changes you have to make it on the FPGAs itself and then convert it into the ASIC by the end. So FPGAs or ASICs are something you're going to involve in order to perform a specific task in an embedded system. So for one specific functionality, you can consider a FPGA or a ASIC, but it is not compulsory for every embedded system. Okay, so this can be one of a component of an embedded system also. Then apart from this FPGA or ASIC, the next important component is diagnostic ports. Okay, nowadays embedded systems comes with a diagnostic port. So what it actually does is it is actually going to check if each and every port of your microcontroller is working fine or not. Any example of a task FPGA does, it can be anything. Okay, so any specific functionality can be implemented on an FPGA. For example, let's say you're going to design an automatic car. Okay, so just an example, you're going to design an automatic car. So you will have multiple functionalities to be taken care of in an automatic car. So you obviously can involve an SOC alone to take care of multiple functionalities. But let's say one specific functionality you want to keep it aside and design it with FPGA. So assume a brake system. So brake system, you are going to take care of it separately with the help of an FPGA. All other tasks you will assemble in SOC. Okay. So one specific task you will implement using FPGA. That is possible. So you literally can implement any specific functionality of your embedded system on a separate FPGA if you don't want to get involved in the microcontroller or SoC. Okay, so that was a simple example. Fine. So talking about diagnostic ports, as I'm saying, in these days, embedded systems comes with a diagnostic port by itself, which is capable of checking if all the ports of the device is working fine. And in some of the cases, these diagnostic ports are also capable of fixing those problems. Okay, so that is also possible. Fixing the problems of the ports is also made implemented in these embedded systems. So diagnostic port also plays an important role. It is going to monitor if every pin of the microcontroller has been working fine or not. Okay, so these are like the most important components of the embedded system. So what happens is, in some of the cases, a board will have a microcontroller or a microprocessor along with memory, FPGA, diagnostic ports, human sensors, ADCs, and DACs. It may not have sensors and actuators in the same board, so you may have to connect it externally. Or you might end up seeing a board which also involves sensors and actuators inside it. Okay, so you may see a board which also involves sensors and actuators. Now tell me, to work all of these components of the embedded system, what is the most important component? SoC contains microprocessor and everything else in a chip. SoC contains multiple microprocessors or multiple microprocessors in a chip. Okay, so I'm telling, apart from this, to work all of this, to make sure all of this is working fine, what is important? First and the foremost thing. So it's the power supply. Okay, so auxiliary system, which means the power supply. And trust me, designing the power supply for any embedded system is the challenging task, because do you think every device in your embedded system works with the same power? Do you think every device in your embedded system works with the same power? No. Some of them work with low voltage, some of them work with high voltage. So if low voltage working device has been provided with a high voltage, the device might get damaged. So it is very important to take care of the power system properly, so that the proper power is being given to any of the device in the network. So power system, auxiliary system plays an important role in designing any of an embedded system. Okay. Now apart from this, these are just the hardwares what you're seeing. Do you think just a combination of hardware performing a specific task is considered an embedded system? Do we consider this? No. So you have to involve the software along. So a combination of hardware and software performing a specific task is nothing but an embedded system. And these are the important components of the embedded system. Is that clear? Any doubt till this? Okay. So this completes the next topic, which is nothing but the embedded systems components. Let us move to the next. So the next we have got is requirements of embedded system. SOC again is multiple microprocessors. Okay. So SOC means it will have multiple microcontrollers or multiple microprocessors involved in a single chip. Okay. So one chip will have multiple microprocessors or multiple microcontrollers. So that is an SOC. So if you cannot handle multiple functionalities in a single chip, okay, so you are going to take more number of microcontrollers. So in order to use more number of microcontrollers, picking more number of microcontrollers is like a challenging task. So you are going to pick a board which has microcontrollers, multiple microcontrollers already connected to each other. So we are going to make use of system on chip if the number of functionalities to be implemented is more. Okay. So let us proceed to the next slide here, which is talking about the requirements of embedded system. Okay, so we have to be speaking about the requirements of embedded system. The very first requirement of the embedded system is reliability. Okay, so you have to make sure that the product you are going to design is reliable. In common, reliability means something which is related to guarantee and warranty. Okay. So let's say you're going to design an embedded system. Okay. And you are selling it to me. Okay. I am the customer of yours right now. You have designed an embedded system and you are asking me to buy that particular embedded system. Now, just because you are a student of mine, so it is a duty of me to trust you and buy your particular product. Okay. So, whatever embedded system you are going to design, so I should definitely be buying it. But after I have bought it, so I am going to buy it based on the warranty you are providing it to me. So, let's say you are going to give me a warranty of 2 years. So, believing that, okay, I will assume that your product will work fine for 2 years of time and I am going to buy your product. So my least expectation is your product is at least working fine for a warranty period you have provided. Now tell me, if your device is not even working fine in the warranty period, do you think I suggest my colleagues or neighbors to buy your particular product? Obviously no, right? So it is very important that at least your device is working fine in the warranty period you have provided. Only then I can ask my colleagues or my neighbors to buy your particular embedded system. So that is really important for you to have a reliable product design. Second, you always have to design a cost effective embedded system because generally whatever embedded system you're going to design, you focus on moderate people. Okay. So you focus on the people who can afford your embedded system. So initially you cannot keep the products like money very high. Okay. So first you have to establish yourself in the market, keeping the price of your product as low as possible so that the middle class people can afford that particular embedded system. So you always have to focus on designing a cost effective embedded system. Then you always also have to make sure that your embedded system is consuming low power. Okay. So you cannot make your embedded system consume as much power as possible. You have to make sure it is consuming very low power. And the fourth point says effective usage of processing power. Actually, if your embedded system is effectively using the processing power, then low power consumption is automatically taken care of. Now, you always have to make sure you are using the processing power on an efficient manner. Now, to show you that with a simple example. So, as I'm saying, it is very important that you are using the processing power in an efficient manner. So, let me go with a simple example. Okay. So, using the processing power on an efficient manner is not always easy. So, it's in fact a difficult job. I'll go with a simple example. Okay. Assume there is a person, a consumer of yours, a customer of yours is coming to you and he is asking you to get an automatic water pumping system design. Okay, this is your requirement. He is asking you to design an automatic water pumping system. And according to his requirements, okay, he wants his automatic water pumping system to be started exactly at 8 a.m. Okay, so you have to start his automatic water pumping system exactly at 8 a.m. for a duration of 1 hour only. Okay, so from 8 a.m. to 9 p.m. you have to turn on an automatic water pumping system. The requirement is very simple. Now, to start with, we have known the components of embedded system. Which one do you think is the most important component here? Which one is the most important component while having an embedded system design? Is it timer directly? So what did we study just now? So what is the most important component even before sensor? What is it? It's a microcontroller. Okay. So it's a microcontroller. So I'm going to choose a microcontroller. So I want to design an automatic water pumping system. Okay. So I am taking a microcontroller as the most important component. So after I have selected the microcontroller, so your microcontroller is supposed to take the action. Okay. So your microcontroller is taking the action. So exactly at 8 a.m. it has to turn on the pump. So I don't know what pump I'm going to use. So as of now, I'm trying to take a high-end automatic water pumping system design. I'm not going to focus on the motor I'm going to use to pump the water. So I'm just taking its driver, which is nothing but relay. Okay. So I am going to instruct the relay. So I'm taking a relay. Okay, this one is the relay here. Oh, relay. Okay. So that's the relay I have taken, which is the driver circuit. Now this microcontroller has to instruct the relay to turn on the pump exactly at 8 a.m. So what do you need to calculate the time so that you're going to turn the relay exactly at 8 a.m.? You need a timer. Okay. And most of the microcontroller will have at least one timer built in. So I am going to make use of a built-in timer which is already available in our microcontroller. Okay. So I'm using the built-in timer. Now assume this automatic water pumping system is being designed to Indian farms. Okay. So it is being designed to an Indian farm. And speaking about an Indian farm, do you think our Indian farms will have a power supply provided for 24 by 7? Will it have a power supply provided for 24 by 7? Obviously, no. So that is why what I'm doing as a intermediate is, so if the power supply is available, the automatic water pumping system works with a power supply. If not, I'm going to provide a separate battery backup for it. Okay. So I'm having a battery connected. Now this is like the high end automatic water pumping system. And also because I'm involving a microcontroller, it also involves a software associated to it. So what this microcontroller does is I'm using the built-in timer of the microcontroller. So timer is going to calculate the time. Exactly at 8 a.m., your microcontroller instructs the relay to turn on the pump. So pump will be on for a duration of 1 hour. Again, with the help of the timer, the microcontroller instructs the relay to turn it off after a duration of 1 hour. So your microcontroller is taking care of turning on the pump at 8 a.m. for a duration of 1 hour. Any doubt in this? Any doubt in this? Okay, no. Fine. Let us proceed. Now we are going to make use of a timer which is built in your microcontroller. Actually, the system which I have designed right now should be working for how much hours throughout the day? The system which I have designed right now should be working for how much hours? Only 1 hour. So exactly at 8 a.m. it has to get the pump turned on, and after a duration of 1 hour it has to be turned off. So my device, whatever I have designed, should be working fine for a duration of 1 hour in that particular day. Now for the rest 23 hours, do you think I can put my microcontroller to the sleep mode? So my motto is to save the power also. Now in the rest 23 hours, to save some power, can I put my microcontroller to the sleep mode? Yes, okay. Now, if your microcontroller is sleeping, do you think the timer inside your microcontroller will be able to count the time? If your microcontroller is sleeping, will your timer still be able to count the time? No. So, because I have taken a built-in timer of your microcontroller, when microcontroller is sleeping, I will not have my timer also running. Now, if the timer itself is not running, do you think your microcontroller will be able to turn on the pump at 8 a.m.? No, again. So, I cannot put my microcontroller to the sleep mode. Just to make sure the device is working perfectly for 1 hour, I have to keep the complete device working for the 24 hours. Do you agree? Just to make sure it is working fine for 1 hour, I have to make sure the complete device is working for 24 hours. Now, do you think I am using the power efficiently? Do you think I'm using the power efficiently? Obviously, no. So, using the power efficiently is always a challenging job. So, what I can do is to make sure I'm using the power efficiently, I'm going to offload my device. I'm not going to make use of the built-in timer. Instead, I'm going to make use of an external clock. Okay. So I'm going to make use of an external clock. Now, the biggest advantage of an external clock is, so I call it as RTC. Okay. So it is nothing but a real time clock. Okay. And the biggest advantage of this RTC is it actually works with very less power supply. And one more biggest advantage is I can separately battery backup it. Okay. So it doesn't have to depend on the power of any other device. You can separately battery backup this particular device. So that's the biggest advantage. Now what I am going to do is I will let my microcontroller sleep, because this time the time is being calculated by the RTC, not the timer which is available in your microcontroller. So the time is being calculated by RTC. So your microcontroller can completely sleep for a duration of 23 hours. So your RTC is counting the time. Exactly at 8 a.m., RTC instructs the microcontroller to turn on the relay, that is the pump. Then after a duration of 1 hour, again RTC instructs the microcontroller to turn off the pump. So now the time is being calculated by RTC, which has been separately battery backed up. I can put my microcontroller to the sleep mode for the rest 23 hours. Now, do you think I'm using the power efficiently? Am I now using the power efficiently? Obviously, yes. So I can put my microcontroller to the sleep mode for a duration of 23 hours, and my device is working fine for a duration of 1 hour, which I was focused on. So I'm going to put my microcontroller to the sleep mode. Okay. So at this time, so I am going to use the power on an efficient manner, which is always a important task. Okay. So that is one of the important thing to be taken care of while having an embedded system design. So apart from that, efficient usage of memory, that also plays an important role. So memory is always a topic of concern when it comes to the embedded system. You will not get enough memory as much as you require. So you always have to make sure efficiently the memory is also managed. Then appropriate execution time. So any embedded system, you have to make sure it is getting executed in the appropriate time. So these are the requirements of the embedded system while you are taking care of it to be designed. I hope this is clear. Can we proceed? Okay, fine. Now moving ahead, the next is challenges you will face. Yes, Vastik, what is the doubt? Laptop is an embedded system? No, that's not. Even your PC is not an embedded system. So they are general purpose system. Why? Because embedded systems are always meant to do a specific task. Uh, you use microcontrollers code in screen. We use MCU's code in screen. That doesn't mean you're considering the laptop or PC as an embedded system. So you're using your computers to design an embedded system. Okay. So computer is not an embedded system in fact, because you're not doing a specific task using your computer. You're in fact doing multitasking in a computer, so it's not an embedded system. So lines of code is also important related to memory. Yes, Prajwal, that is important. So as the number of lines will be less, your memory occupancy will also be reduced. We use embedded code in power management of laptop. Not just in the power management to make sure your laptop is working fine. Yes, you have device drivers which runs on the hardwares. So they are like the programs. As I'm saying, you're doing multiple tasks on a laptop. Okay. So when you are focusing on doing multiple tasks on one particular device, you don't consider it to be an embedded system. So an embedded system is always meant to do a specific task. For example, you take a washing machine, its specific task is to wash the clothes. Okay, you will have multiple functionalities, but it has a specific task to do. If you take an oven, its task is to heat the food. If you take a car, its task is to uh, uh, make you reach to a particular destination. So for every embedded system, there will be one specific task provided. So your laptop doesn't focus on doing one specific task, so it's not an embedded system. Mobile phone actually is not an embedded system, but we have a reason for putting it under embedded system. And as I said, we will revisit that statement of mine when I discuss things with respect to general purpose system versus the embedded system. So there you will get a clear picture of why is mobile phone put under an embedded system. But in fact, it is also a general purpose system. Okay, I hope no other doubts. So we are going to the next slide of ours, which is nothing but the challenges of the embedded system. Okay. Now coming to the challenges of an embedded system, the very first challenge is an efficient input for the output. This is in fact a challenge which anybody will face while having an embedded system designed. So getting an efficient output for an input you are providing is always a challenge. Let me go with a simple example for that also. Now assume you have a microcontroller. Okay. Assume you have taken a microcontroller, and to this microcontroller I will have a switch connected. Okay. So to this microcontroller I will have a switch connected. Now I don't think you have known a switch. If you have known, it is well and good. So this is how we represent a switch. Okay, one second. So this is how a switch is represented with two notches and a standing line. Okay, this is a switch. And one end of the switch is being connected to the microcontroller. Another end of the switch is being connected to ground. Okay. So here I'm going to take a notch. So more about switches we are going to learn in detail. This is just an example to show getting efficient output for the input you are providing is really important. It's a challenge. So this is how we represent a switch digitally, and this switch is said to be open. Okay, because there is no connection being made. So the switch is said to be open. Now, if the two notches are connected by the switch like this, then we call it as switch being closed. Okay, so this is switch being closed. Okay, this is a microcontroller I have selected. There's no specific microcontroller's name I'm taking. I have a switch here. Can you look at the switch and tell me if the switch is open or closed? Look at the switch and tell me if it is open or closed. Okay, so the switch right now is being opened. Now assume I'm going to press the switch. So I'm closing the switch like this. Okay, so I have closed the switch now. Switch is being closed. Can you tell me what are you going to read at this pin of the microcontroller? If the switch is closed, what are you going to read at the pin of the microcontroller? Okay, is it a 1? All right. So please understand, whenever you want to specify ground, okay, so microcontroller can only understand things in terms of zeros and ones. So whenever you want to refer as ground, you have to say it as a 0. And whenever you want to specify 5 volts or VDD or VCC, okay, you can say it as 1. Okay, whenever you want to indicate ground, it is 0. 5 volts or VDD or VCC, you can say it as 1. Now tell me, what are you going to identify here? Come on. Yes, so you are going to identify a ground because the circuit is being complete. From the microcontroller, the line is being connected to ground. So the pin of the microcontroller identifies a ground. So ground represents 0. So whenever the switch is closed, I'm going to read a 0 at the pin of the microcontroller. Correct? Now coming back, okay, whenever the switch is open, what do you think you're going to read here at the pin of the microcontroller? So now the switch is open. So if the switch was closed, the circuit was connected to the ground and you were able to read a 0. Now how will you still be able to read a 0? Is the connection being complete to the ground? Do you see a complete connection made to the ground here when the switch is open? No. Then how will you be able to read a 0? but no input voltage also, correct? So yes, we don't have any input also provided. So this switch is called as a open line. Okay. So this switch is called as a open circuit, and we also can call it as a open line, or we call it as a floating line. Okay. So when the switch is being open, the circuit is not complete. So it is leading to something called as the floating line. Now the problem with this floating line is, remember, this floating line can get the noise around it attracted. Okay, this floating line can get the noise around it attracted. Now, due to the noise or electromagnetic waves being attracted by this floating line, you might end up reading a 1 at the spin of the microcontroller. But do you think that is a valid one you are seeing here? Is it a valid one you are seeing here? The line when it is open is a floating line. So due to the floating line, there is noise and electromagnetic waves being attracted, and you might end up reading a 1. Okay, and that one is not a valid one which you are reading at the pin of the microcontroller. Now, did you get an efficient output for the input you provided? Did you get an efficient output? So no, that is not an efficient output because you did not provide a valid input. Okay. So yes, the behavior is undefined. You might end up getting a 0, or you might end up getting a 1 due to the noise around it. So this is not an efficient output for the input you are providing. Now to make this output efficient, I am going to add a pull-up circuit. Okay. So it has to be a pull-up circuit. You are going to add it here. Okay, so more about the switches, pull-up circuits and all you will study in the coming classes. So I am going to add a pull-up circuit with a resistor like this. So now what happens is, okay, so this time you will get an efficient output for the input you are providing. So whenever the switch is closed, okay, whenever the switch is closed, so what happens is, you are going to read a ground. Okay, so whenever a switch is closed, I would say, I will mark it in a separate color. So whenever the switch is provided with ground, madam, internal pull up or pull down is there. So that depends on the pin of the microcontroller. So some of the pins of the microcontroller you are going to select will have an internal pull up or pull down already available. But if it is not there, you will have to add it externally. It completely depends on the microcontroller you have selected. So assuming it doesn't have a pull up or a pull down circuit, so I'm going to add it externally. So if the switch is closed, remember the current from the current is going to flow to the ground like this. Okay, when the switch is closed, now current from VDD is flowing to the ground. So you will be able to identify a ground here, hence a 0 will be identified. And if the switch is open, so current from the VDD is flowing to the microcontroller, and you will be able to read a 1. So it is no more a floating line. Now you have added a pull-up circuit. So due to the pull-up circuit you have added, you are going to end up reading a 1 at the pin of the microcontroller. So this is an efficient output for the input you are going to provide. Understood? So it is always a challenge to get an efficient output for the input you are providing. Okay. Now the second challenge you are going to face while having an embedded system designed is embedding an operating system itself. Okay, so it is always a challenge to have an operating system installed in any of the embedded system you are designing. That is because sometimes you may pick up an operating system which is already available, and sometimes you may try designing your own operating system. Now, while the operating system is being designed, you have to take care of its subsystems. So, like, let's say process manager, then you have to take care of memory manager, you have to take care of the driver manager, you have to take care of the file system manager. So, you have to take care of multiple subsystems of the operating system. And embedding an operating system is always not easy for an embedded systems design. So that is also a challenge. And coming to the code optimization, again, it's a challenge because having an optimized code is really important. So writing an optimized code, especially when it comes to the embedded system, is very important. And that comes only if you have good practice of programming. So any programming language, you should have a good practice. Only then you can have an optimized code written. And optimization means in what factor am I going to say the code is optimized? On basis of what can we consider it's an optimized code? Yes, so it is the time, okay, and also the space complexity. So optimization is always taken with respect to the time and the space complexity. So time complexity means uh, it is like you are going to consume how less time. Okay, so you have to make sure your embedded system is taking the action in very less time. Okay, and space complexity is your code should take very less space. So that is space optimization. So less memory and less time for the execution of the code. That is when you call it as an optimized code. So that is again a challenge, having an optimized code written. And one more challenge is testing and debugging. So that's like a very big challenge and a very important challenge whenever you are trying to design an embedded system. So that's a very important challenge. That is testing and debugging. Now, every product you design should be tested, and if there is any problem, it needs to be debugged on time. Now, one big example for testing not being properly made, okay, means let's say, have you heard of a problem of a nano car? Like, have you heard of any problems of a nano car? And if yes, what do you think it is? Any problem of a nano car? A battery burn, yes. Air conditioning is okay. So the main focus of Tata company was to make sure the middle class people can afford a car for themselves. So his focus was to bring a affordable car for the middle class people into the market. So he was in a very hurry to enter the market first, that he failed to test each and every product being designed thoroughly. Okay. The Tata company failed to test each and every product thoroughly. I'm not saying every nano car's battery had a problem. So very few of the cars would catch fire while it is being on the road. So due to some problem with the engines or with respect to the batteries, or it can be anything. So that is like a failure of not testing testing the product properly. So every device was not thoroughly tested, for which some of the products caught fire while being on road, and that was a huge impact to the well established Tata company, isn't it? So that was a very important thing to be tested. Every product had to be tested. But that was like a drawback for the Tata company when such cases got identified. That is one of an example. Another example, if I take, have you heard of a problem of Samsung Note 7 phone? Have you heard of a problem of Samsung Note 7 phone? If yes, what is it? No? Yes, again. So that was a battery bust. Okay. So yes, the device was overheating, and some of the phone's battery got blasted while it was being used. And that was also a problem of not testing the product thoroughly. In fact, when that kind of a issue was appearing in the day to day life, so we had a message in the plane tickets also saying people carrying Note 7, Samsung Note 7 are not allowed to board the plane. So something like that. So it was a very serious scenario. So you couldn't allow a person who was carrying a Samsung Note 7 phone because it can get blasted any time. And that was again a hit to the market of the Samsung company. Samsung, being a well established company, still went down for a time being because the Samsung Note 7 was not tested thoroughly before it is being brought to the market. So every product's testing is really important when it comes to the design of an embedded system. I mean, I'm not talking about the testing of an embedded system. I'm just telling in general that testing plays a very important role while having an embedded system design. And one more example is your Apple phones, okay, iPhones. So if you observe the iPhones these days, they comes with their own map. Have you noticed it? So they don't have the Google Maps, in fact. So they have their own built-in maps available. Have you noticed? If not, okay, let me tell you. So these days the iPhones comes with their own maps. Okay, so they are not using the Google Maps. So people were not convinced with the UI, the user interface, the graphical user interface of the maps. So many people are so much used to use the Google Maps. Now, if you suddenly put up an application called Maps, which is not people are happy using, so people started asking for Google Maps to be brought back. Okay, so people literally started asking for the Google Maps to be brought back, and that was again due to the problem with the uh, graphical user interface. People were not ready to use the maps which iPhone people literally gave. So they did not test, they did not take the opinion of much of the people while it was made to be put on the device. So that is again a failure of not properly testing and debugging. So this way, testing always is a challenge while having an embedded system design. So you have to take care of all of these challenges with respect to having an embedded system design. Nokia Android was to a big failure. Okay. So it is not like the product itself is a failure. It's like uh, due to the proper testing, even after having a good product design, if you lack the proper testing, then it is still considered to be a failure. Okay, whether to a well established company or to a uh, startup company. So testing is always very important while having an embedded system design. Okay, so yes, these are the challenges you might face while having an embedded system design. I hope it is clear. Moving to the next, we have got is trends in the development. Okay, so different trends we have got while having the development done. First one is processor trends, means like choices or options you've got. So obviously processors have got more of the trends these days. So depending on the situation, depending on the requirement, you can pick a particular processor. So some of the processors will come with built-in ADC. Do we need assembly language here? No. So we are going to make use of the C programming language itself. Okay, I was talking about the processors. So processors are going to uh, have so many trends these days. So you can pick a processor having a ADC built in. You can pick a processor which will support Ethernet if required. You can pick a processor which supports image processing if required. So it completely depends on the reason or the requirement you are designing a embedded system. So processor has a lot of challenge, lot of trends available in the market. Apart from that memory, you already know you have got so many choices in the memory when it comes to the memory of the embedded system. So, for example, if you want, you can choose any of a memory which belongs to ROM. You can choose any of a memory which belongs to RAM. You can choose any of a memory which belongs to a hybrid memory. So, you already have got a choice, multiple choices. Depending on the requirement, you can choose the memory also. Then coming to the operating system, again, you have got choices. You can go for a paid operating system like Microsoft Windows. You can go for a free operating system like Ubuntu or some Linux based operating system. You can choose. Then programming language, you have n number of options in programming language. Every day there is a new programming language being introduced. So there is C, there is C++, Java, Python, .NET, SQL. So whichever programming language you are comfortable with, you can choose that programming language. The only challenge is you have to also pick the corresponding compiler or interpreter which converts your program to a machine understandable language. So that is also a challenge. Okay. So you can pick any of a programming language, but you should have a proper interpreter or a compiler which is capable of converting that to a machine understandable language. So that is a challenge. Apart from that, development tools. So some software, some applications you have like n number of applications in the market, which you can choose according to your requirement. That also comes with paid and unpaid version. So whichever you are okay with, you can choose the development tool also. The other next we have got is common design matrices of embedded systems. So let me also talk about this quickly. So time to prototype. Prototype. What do you mean by prototype, by the way? What do you mean by prototype? A sample, correct. A sample working model, a basic working model, I would say. Okay, so that is a prototype, in fact, when it comes to embedded systems design. And we always suggest not to consume more time to have a prototype itself designed. If you consume more time to have a prototype itself designed, it hits the time of market at the end. So you shouldn't waste much of your time in just designing a sample model. Okay. Because by the time you hit the market, there can be another company who has already taken over the market. That is still possible. So you should not waste much of your time in just designing its prototype. Then you have to make sure power is managed efficiently. The different devices work with different power consumption, so power should be managed efficiently. Like you have to make sure every device has been provided with the required voltage only. So providing more can damage that particular device. So power has to be taken care of. Performance and correctness, obviously your system should perform fine according to the expectation. It should be working correct, and you have to make sure time and space is properly uh, consumed. Then size, it completely depends on the requirement. If you can have a smallest to smallest embedded system design like that of your Bluetooth, or you can have biggest to biggest embedded system design completely according to the requirement. The size also have to be taken care of. Then NRA is non-recurring engineering cost, which happens unexpectedly. So that is not something which happens every time. So non-recurring engineering cost is like some problem you may face. Okay. So to make you understand non-recurring engineering cost, assume yourself as a manager as of now. Okay. So assume you are a manager of a team. There's a customer who comes to you and he asks you to design X, Y, Z product. Okay? So he is asking you to design an XYZ product. So he in fact is giving you sound is left. Somebody is on. Oh, got it. Lahari, your mic is on. Please can. Excuse me. Is it fine now? Okay, so Lahari's mic was on. Guys, please make sure you're taking care of your mic because it causes a disturbance to the class. Okay, I was telling with respect to NRE, which stands for non-recurring engineering cost. So assume you are a manager of a company, a client comes to you and he is asking for you to design an XYZ product. Basically, the product is involving three parts, X, Y, and Z. And he's saying at the end, he will choose according to the outcome of the product you have designed. So what you do is you being a manager will hire three engineers, engineer A, engineer B, engineer C. So because you are a manager, you will hire three engineers. So engineer A is going to work on part X of the project. Engineer B starts working on part Y of the product, and engineer C is going to work on part Z of the product. So engineer A is working on part X, engineer B is working on part Y, engineer C is working on part Z. Now each of the engineers worked on the parts you had provided, and you being the manager will assemble X, Y, Z parts to make one project and hand it over to the customer. Now you being the manager paid uh, A engineer with around let's say 10,000, B engineer with 7,000, and C engineer with 5,000. Okay, just an assumption. You being a manager paid 10,000 for A engineer, 7,000 for B engineer, 5,000 for C engineer. Now overall cost is around 22,000 if I'm not wrong, yes. So the overall cost is 22,000. Okay, what you invested on making an XYZ product. But to the customer, you are going to say 25,000. Okay, because you are a manager, you have to keep your profit share also. So you are going to cost 25,000 for the customer. Now this customer comes and sees just the X and Y part is so much sufficient. So he will assume, he will think, for me only XYZ is so much sufficient. He doesn't want the Z part. So he will say, I'm going to buy only X and Y product, paying you 15,000. Okay. So he is telling, I'm going to pay you 15,000 only. Okay. Or let's say some 18,000. Okay. Just assume he's going to pay you 18,000 and buy your X and Y part only. He will not accept the Z part. Now the investment what you being a manager made was 22,000, but you earned was only 18,000. How much is the loss? The loss itself is 4,000, isn't it? So you are seeing up a loss of 4,000. And this loss is something called as non-recurring engineering cost. Okay. So this can be possible in some of the cases. I'm not saying it happens in all the cases. This can be a possibility in one of the cases. So you should be able to face the loss also while having an embedded system design. Then maintainability and flexibility, you always have to make sure your device is maintainable by the common people. It is made flexible also. So it's like if one particular part of your product is not working fine, it should not affect the other parts. At least the other parts should be working fine, apart from one which is not working fine. So you have to make your product easy to maintain and it is flexible. Then safety always plays an important role. So it is very important that your uh, products are made human safe. So you cannot harm human life while handling this particular embedded system. Then unit cost, as we already spoke, we have to keep the cost of the product as minimum as possible so that the common middle class people can afford it. And time to market, you make sure you are up to the time of the market, and you should be the first one to occupy the product, and you have to make sure the product is been working fine in the market. So these are the common design matrices of the embedded system. Is that clear? Okay. So the next we have got is few more simple parts of the theoretical things. So which we will do it in tomorrow's class. It's already time. So tomorrow also, because you have got a placement meeting, so we are going to start the class a class a little late. So till 7 you will have the placement meeting. So we can start the class at 7:15 tomorrow as well. Okay. So tomorrow for the first 1 hour, we will have some theoretical parts. Then we will start with the programming part. Okay. So if possible, we will start with the basic idea of programming in tomorrow's class. Hope the class has all been clear. If you have got any doubts, let me know. And here is your QR. Please have your attendance mark and then quit the session. Thank you all. We'll continue tomorrow. Okay, any problem. MC module is not opening for me. I'm unable to mark the attendance. Okay, Divakar, are you new to this particular batch, like 22028 or 23008 and 23011? If yes, then your name must have been missing from the list of attendees. You have to reach out to our student counselor Anusha or Deepak sir. So either of them will be able to put you into the list and you should be able to use it. So please reach out to either of them and they'll help you out with it. Okay. Others, please have your attendance marked and then quit the session. And what is the difference between embedded C and advanced C? Uh, Divakar, you have texted already. Okay, I will inform them and make it happen. Okay, what is the difference, main difference between embedded C and normal C? Not much of a difference actually. If you see the programming part, it is very same. There is nothing different we are going to use. The only thing is not 100% of the C programming will help you here in embedded C. Okay, so we generally don't use printf function. We generally don't use scanf functions. We don't use some of the built-in functions of C. Okay, so ideology of using the program is the same. Programming language remains the same, but we don't use much of the built-in functions here in the programming of an embedded system. So we name it as an embedded C. That's the only difference. Between C and C++, C is like a basic language, C++ is the advanced language. We have got multiple other features in C++, like as inline functions, different kind of like the pillars of C++ you have already known, which will not happen in C. So advancements of C, you can see it in C++. C naming variable convention that remains the same here also in the embedded C. So that is not going to vary. Okay, fine. So thanks for attending today's class. We'll continue tomorrow. Thank you all. Yes, Kalyani, have you got any doubt? If it is with respect to attendance, attendance is not marked. Okay. So like I have still got the QR given here.